Okay, next we'll take a look at the basic techniques that we use for manipulating asymptotic expansions to derive accurate and concise estimates of the quantities that we're trying to study. So our goal is to develop an expansion on the standard scale for any expression that might arise in the analysis. And these are just examples of the kinds of expressions that might show up. Some of them are artificial, but some of them actually turn up in our analysis. So we saw 2n choose n when studying the Catalan numbers. And the problem with some of these, like 2n choose n, it might be hard to compute that. So imagine a 17th century mathematician trying to compute that for n equals 1,000. That's a lot of multiplications. Or imagine a computer programmer today, give them the job of computing that. It's simple to define, but if you use the basic definition for n equals a million factorial is a pretty big number, so you have to deal with it in some way. On the other hand, using asymptotic expansions, we're going to get all of these in a kind of coherent form where we can be confident that we can work with them. So there's a lot of different techniques that we use, and each one of them is relatively simple, but it's still worthwhile calling out examples of each. So, and we'll look at each one of these: simplification, substitution, factoring, multiplication, division, and composition. They seem really simple to call out, but on the other hand, when faced with dealing with one of these functions, you really want to think in terms of, there is an easy way to do this, one of these basic ways. Just have to figure out which one it is. And there also the X-log trick is an important one, or technique, and I'll show that in a minute. So again, the whole idea is that a lot of times we have not just these quantities, but maybe they combine in some way. So like, what's the value of 1 over 4 to the n 2n choose n? That's an expression that arises that's of importance in the analysis of algorithms. And if you ask a programmer to try to compute that for n equals 10 to the 6, it's going to be a challenge. And we'll actually see that it's relatively simple to express this in terms of standard functions via asymptotics. And all of these functions and all of the functions that arise, we can do that. So let's take a look at the various techniques. So the first thing is that an asymptotic series is only as good as its big O term. So that means there's no point in carrying around smaller terms. If you have something that's encompassed by the big O, just drop it. It's only going to make the calculation more complicated, and it's not helpful in any way. So we don't write log n plus gamma plus O of 1 where gamma is a constant, because the O of 1 says the error is bounded by some constant, and so that constant might as well be gamma or whatever. It's better to say that write down this expression as log n plus O of 1. It's more compact. The other idea we already talked about was substitution, where you can just change variables in a known expansion. So the Taylor series for log of 1 plus x is x minus x squared over 2 plus x squared over 3 and so forth. And if we just plug in a different value for x, we plug in 1 over n, then we get the expansion. So that's one technique that we already used. Factoring, a very common thing to do is to estimate what the leading term is, then factor that out and expand the rest. So look at this function, 1 over n squared plus n. And we think to ourselves, what's this going to be close to when n is large, like n is 1,000,000? It's going to be close to 1 over n squared. So we might as well factor out the 1 over n squared. And then in this case, what we're left with is 1 over 1 plus 1 over n, and that's a geometric series. And we have asymptotic expansion for the geometric series. So expand it, since it's 1 plus 1 over n, it's 1 minus 1 over n plus O of 1 over n squared. And we could take that to more terms if we wanted to, but that's an asymptotic expansion of that. If we use that expansion, it says that for n equals 1,000,000, that value is going to be very close to 1 over n squared. The relative error that we would make would be 1 over n in that 1 over 1,000,000 in that case, which is probably small enough for our purposes. You distribute that, so it's 1 over n squared minus 1 over n cubed plus big O of 1 over n to the 4th. That's a asymptotic series in the standard scale for 1 over n squared plus n, very easy to obtain. Multiplication. So multiplication is just algebra, but also employing simplification. When we have smaller terms, we throw them out. So let's look at the square of the harmonic numbers. So we did an estimate of the harmonic numbers. We talked about the asymptotic series for the harmonic numbers is given by approximation with a sum, and I talked briefly about that. And we'll talk more about that kind of asymptotics later. So the harmonic number is approximated by log n plus gamma plus big O of 1 over n, where gamma is Euler's constant, 0.577. So to compute the square of the harmonic numbers, we have to square those. So that's two terms with two factors with 3 terms each. So we're going to wind up with 6 factors when we add all that together. So log n times each one of those, log n squared plus gamma log n plus big O of log n over n. Inside big O, we usually don't specify the base of the logarithm since it only differs by a constant. So it doesn't matter that it's natural log. So we just write log. This means it's not specified as some constant. Then the next row is gamma times each one. Gamma log n plus gamma squared plus big O of 1 over n. And the next term is O of 1 over n times all of them. O of 1 over n log n over n, gamma times O of 1 over n is O of 1 over n, and O of 1 over n times O of 1 over n is O of 1 over n squared. So that gives us 9 terms, but we can throw a lot of them out because, well, first of all the big O terms, you just pick the largest one. So big O of 1 over n squared is much smaller than log n over n, so it can be subsumed in that. Same with O of 1 over n. So all the big O terms, and there's 5 of them, get subsumed in that O of log n over n. There's the gamma squared, and then gamma log n appears twice. So that's an asymptotic series in the standard scale for the square of the harmonic numbers. Now, just taking a look at this series, it's important to note that there's a difference between the first couple of terms and the big O that we lost. So log n squared, so n is a million, log n is going to be some small integer. So log n squared and 2 log n they're not that far apart. So it seems like we're going to need those. And then gamma squared is a constant, but log n is a small integer. It's only a slight improvement in precision to carry on those terms. And so we're probably going to want those terms. But when we get it divided by n, that's when we have a huge improvement in precision. Now, you can't always tell ahead of time how far you have to go to get this big improvement. But in real problems, usually happens after 3 or 4 terms. And that's what happened here. If you look at a table of these quantities for n equals 100, 1,000, 10,000, and 100,000, you can see. So hn squared is the quantity that we're trying to estimate. And then if you just tried to estimate it with log n squared, you can see you'd still be off by a fair amount, 10% for even 100,000. If you add the 2 gamma log n, you come much closer. And add the gamma squared, actually we're accurate to 3 decimal places. Because the next term, the one that we're missing, is going to differ. It's going to be bounded by a constant times log n over n, and for 100,000, that's going to be out in the 4th or 5th decimal place, assuming the constant's small, which normally we assume in these asymptotic series because they are. but we can check, as in this case, that that's an accurate approximation. So usually we'll try to carry it out long enough until we get this big improvement in precision. All right, division, that's like multiplication. So let's look at this example. Hn equals natural log, Hn over natural log of n plus 1. So what we'll do for that is we'll expand the numerator and the denominator, both, and then we'll use the geometric series to expand the denominator, and that'll give us a multiplication problem. So let's look at how that works. H of n is log n plus gamma plus O of 1 over n. That's the approximation that we've been using for H of n. Natural log of n plus 1, factor out a log n, and it becomes natural log of n plus natural log of 1 plus 1 over n. Natural log of 1 plus 1 over n is big O of 1 over n, just from Taylor. So now we have the ratio of two asymptotic series, and what we'll do is factor out the log n as before. So let's divide both numerator and denominator by log n, and so the numerator becomes 1 plus gamma over log n plus O of 1 over n. It's over 1 over n log n, so we're simplifying that. And then the denominator becomes 1 plus O of 1 over n. We could make it 1 over n log n. We're making it a little bit bigger. And again, that's just to simplify the formulas. If we did not get a sufficiently accurate estimate, we could go back and try to correct that. And now 1 plus O of 1 over n, if you expand as a geometric series, it just becomes 1 over 1 plus O of 1 over n is 1 plus O of 1 over n, just as a geometric series. And again, if there are more terms, you could carry more terms out there. So now we have a multiplication problem, and if we multiply that out, that's a proof that the asymptotic expansion of Hn over log of n plus 1 to within O of 1 over n is 1 plus gamma over log n plus O of 1 over n. And again, there's a big improvement in precision when we get to the 1 over n term, so this is going to be a very accurate estimate of that more complicated quantity as n increases. Composition, so this is similar, we're just going to substitute an expansion and figure out what to do. So if you had to compute e to the h of n, you plug in the expansion for h of n and see what you get. What you get is e to the log n plus gamma plus big O of 1 over n. E to the log n, that's n. E to the gamma is e to the gamma, that's a constant. And then what's left is e to the big O of 1 over n. And then that one you expand with Taylor, although it's a little more work to actually prove that, but you can from now on use that lemma. E to the O of 1 over n is 1 plus O of 1 over n, and then that'll, and you can expand it a couple of terms if you need to, and that gives the simplification that e to the hn is n e to the gamma to within 1 over n, or n e to the gamma plus O of 1. And again, n e to the gamma, that grows with n. O of 1 is a constant, so there's a big change in precision. So that's going to be a very accurate approximation for large n. Each time that we do an asymptotic expansion, we go down to where we can usually try to go where we can get a big improvement in precision like this, and gives us a simple expression in terms of familiar functions for this thing where otherwise its growth might not be so obvious to see. And again, you can see for n equals 1,000,000, this is accurate to within 1. Absolute 1, which is a fine, small relative error. Xlog trick. This is a way to bring us in a position where we can apply the composition in more complicated scenarios. And all we'll do is write f of x as e to the log of f of x. Then we can expand log of f of x, and we can expand e to that series as we did before. And here's a fine example, 1 minus 1 over n to the n. And when you see a thing like that, you have to think, how would you compute that for large values of n? Ask a programmer to compute that for n equals 1,000,000. It's maybe not necessarily so easy to do. It's going to at least take time proportional to n, and there might be precision problems, or as with factorial, there might be problems in needing to carry too many digits. Well, actually, the way people compute things like that is use the Xlog trick. So that is, we write that as e to the log of 1 minus 1 over n to the nth. And so the log of 1 over 1 minus n to the nth, we can bring the n down. It's n times the log of 1 minus 1 over n. And so now if we expand log of 1 minus 1 over n, again using the Taylor series, we get minus 1 over n plus big O of 1 over n squared. And then do the algebra, that's e to the minus 1 plus big O of 1 over n. And again, e to the O of 1 over n is 1 plus O of 1 over n, so that's 1 over e. It says that that function, 1 minus 1 over n to the n, is going to be very close to 1 over e. And again, that's the big improvement in precision we always look for. And again, we can check that for n equals 1,000,000. That's accurate to 6 decimal places. Because the big O says that the error is going to be out there around the 6th decimal place. Again, when we're trying to understand what the value of the quantity is, if we know that it's 1 over e, which is this constant, 0.367879, that's very precise and concise information, as opposed to that exact expression, which maybe it's hard to know what it is. And when we start combining these kinds of formulas, which we do all the time, we're going to want to work with the precise and concise expressions. So that's the Xlog technique, and we actually use that one quite a bit. Thinking about these various techniques, here's just a couple more examples that you might want to try doing to make sure that you understand the kinds of techniques that we're using. So log of n over n minus 2 to within 1 over n squared, and hn squared, what's that constant times the 1 over n term, because we only got it to log n over n. And that's just to illustrate that if desired, we can go to more asymptotic accuracy. Maybe we need to do that because we've got a function where we're multiplying that thing by n squared, and so we need more accuracy, just for example. For log n minus 2, what we do is factor out the n, so that's the leading term, and then we have log of 1 minus 2 over n, and then just expand the rest. And so it's minus 2 over n plus big O of 1 over n squared. That's the solution to that one. And this one is just carrying out the asymptotic approximations to one more term, which is 1 over n squared term. And then that gives the coefficient of log n over n is 1. And again, these types of things, as with any kind of mathematics, they require a little bit of practice. But the techniques are so simple, it's not difficult to learn how to do these kinds of expansions. So that's a quick introduction to manipulating asymptotic expansions.